Hi there, this lesson is on bond enthalpy calculations, which are the second type of calculations that could be required for this unit. Essentially what this type of question is wanting is for you to use bond energies that they will supply in the question. And bond energies are, what it means is that it's the energy that's required to break bonds of that type. It's always given a positive value as bonds take energy to overcome. That's because they're more stable bonded than unbonded, so it requires more energy to be broken. The calculation that you're going to use is summarised by this little sentence here. Bond BB minus BM equals delta H. So bonds broken minus bonds made equals the change of heat or enthalpy of the reaction. So you could remember BB minus BM with something silly. Off top of the head you could think of Breaking Bad for BB. Breaking Bad minus baking meth equals heat. So Breaking Bad minus baking meth. Somehow to remember that it's the bonds broken that comes first and you're subtracting the bonds made. So you're going to add up all the bonds broken and you're going to add up all the bonds made and you're going to subtract one from the other, and the result is going to be your delta H for the reaction. In order to do this calculation, you'll need to draw stick diagrams of all the molecules involved in order to count all the bonds broken or made. This is called structural formula. Oops, there's a typo there, that should say structural. So for example, CH4 is a molecular formula and a structural formula would look like this. So you should remember these from year 11. I would call them stick diagrams. And in order to know how many sticks to put in your stick diagram, you need to be aware that the valency of the element involved tells you how many sticks that it will need. So for example, oxygen's got 6 valence electrons. It's in group 16. Just like you worked out Lewis dots, that it's got 6 electrons in its outer shell. You'll also know that it needs to form 2 extra bonds so that it gets 2 more electrons to make 8. So oxygen will always have 2 sticks. Carbon has 4 valence electrons, so it needs to make 4 more bonds to get 4 more electrons to make its 8. So carbon always has 4 sticks. Hydrogen always has 1. Nitrogen always has 3. So if you look at this stick diagram I've done up here, you can see that hydrogen has 1 stick attached to it in each case, and carbon has got 4 sticks. So you know that you've done it properly. Now if we were trying to draw a stick diagram of carbon dioxide, we know the symbol for that is CO2, don't we? And carbon dioxide, like a Lewis dot diagram, you're going to put the C in the middle because it's written first, and then you're going to put the oxygens on either side. And because we know every oxygen needs 2 sticks, we're going to make these double bonds. And if you look at carbon now, you can see that carbon's got 4 sticks. So that's a good diagram. For O2, if we just did that, we would know that was wrong because carbon has to have 2 sticks. So it needs a double bond. So here's a typical exam question. Use the following average bond dissociation energies, or bond energies, to calculate the standard enthalpy of combustion of methanol. So basically they want you to calculate the delta H of this reaction. And they've given us the bond energies, and notice that here the O to O bond is 157 and the O double bond is 496. So you can't just use a single bond or double a single bond energy to get a double bond energy. A double bond takes more than that energy, more than double the single bond energy. So that's why it's important to get the sticks done right for our calculation. Now, the first step in one of these calculations, step 1, is always to draw the stick diagrams so that you can see the bonds broken and the bonds made. So firstly we've got methanol. So that's 1 carbon in the middle, 3 hydrogens off it, and an O and an H. That's an O bonded to an H, so that's sticks. So you can see carbon's got 4 sticks off it, each hydrogen's got 1 stick off it, and the oxygen's got 2 sticks off it. So we've done that correctly. We've also got 3.5 oxygens as a reactant, so we're doing all the sticks for the reactants on this side. So we've got O2, we've got 3/2 of them, in other words that's 1.5, isn't it? So we've got 1.5 of those. And over this side, for the reactants, products. What am I saying? Products. We have CO2, so let me draw it like I've discussed on the previous slide, and we've got H2O. So H2O is going to look like this, which you will be used to drawing as a Lewis dot diagram. And because there's 2 moles of it, I'm going to draw it twice. I didn't draw this one 1.5 times because that was just a bit tricky. This oxygen over here. Okay, so now we're just going to basically number crunch. So we're going to total up the bonds broken, and we're going to total up the bonds made, and then do our BB minus BM, Breaking Bad minus baking meth, equals delta H. So we have to look at these reactants and look at all the sticks that have got broken in order to make carbon dioxide and water. Firstly, we've got C to H bonds, and as we account for them, if we just go through with another colour pen and just cross them out. So C to H bonds, we've got 1, 2, 3. So we're going to put times 3. We've got C to O bonds. How many of those? We've just got 1 of those. We've got an O to H bond. and we've got only one of those, and we've got lastly an O double bond O bond, and that's times 1.5. So then we're going to look at our table and just add up all of those numbers. So if we look at the table for C to H bonds, the number's 412. So we're going to have 412 times 3. The C to O bond is 360, so 360 times 1. And the O to H bond is 463. And the O to O bond is 496. It's the double bond one that we're after. 496 times 1.5. So we can throw that in our calculator, and the total should be 2,803. For the bonds made, we've got C double bond O bonds and the carbon dioxide, and let's just cross them out. We've got 2 of those, so we need to multiply that one by 2. We've got in the water O to H bonds, and counting them, we've got 1, 2, 3, 4. So that's times 4. So it's quite important to draw the 2 waters, so that, and by crossing out the sticks, this water one would commonly be mistaken for only 2 OH bonds, but because there's 2 molecules of it and each molecule's got 2 of these bonds, we need 4. So we look at our table and find the C double O bond is 743, and we need 2 of those, and we need to add the OH bond, which is 463 times 4. So we add all of that up in blue, and that totals 3338, and now we can do our BB minus BM is 2,803 minus 3338, and gives us our final answer of minus 535. And the units you will need to write for excellence, so 3 significant figures and units: kilojoules, little k, big J, and it's per mole, so MOL minus 1. Now, because it's minus, remember that means it's an exothermic reaction. So there's the answer in more neat type, and here's some practice questions in your workbook. And you'll notice that on page 56, this one's a little bit different. In this question, they've given you the delta H, and they've asked you to find out the value of an OH bond. So you're going to need to make that X the unknown number and rejig this whole equation to give x equals, which requires some mathematical skill. But I'm sure you're up to it. So have a go at those questions. And that's the end of this lesson.